Okay, well, it is Tuesday and it is noon, which means that it's time for Research for Social Change seminar. And this week, we actually have a guest who is here from the Viterbi School of Engineering. Dr. Kejriwal is part of the ISI as well as the Industrial and Systems Engineering, and he is going to be talking with us about advancing computational social science research through text and network analytics. So any of you who know my work know that this is the sort of thing that I personally really like, and I'm glad to see some folks here and more folks showing up online. So without much more ado, I'll just turn it over.
All right, thank you everyone for coming. I'm delighted to be here, and there are a bunch of things that I want to show you today, but it's really more of a conversation and discussion. I'll start with some of the work that I do, example projects and so on, but maybe we can leave some time, 5 to 10 minutes in the end to hear about what you're doing and whether there's chances for synergy between our disciplines. All right, so this is just a little bit about me. So I am based out of both the Department of Industrial and Systems Engineering and also at the Information Sciences Institute, which is in Marina del Rey. So I run a group called AI and Complex Systems, or AICS. I come from a computer science background, but I've kind of been all around the School of Engineering. And I have a deep interest in computational social science. So this is sort of my passion area, where we're trying to use computation and AI in service of social science problems. And you'll see some examples today. So we care less about the tools almost, the methods. We're more interested often in the scientific questions, but we also like to build tools and algorithms for solving some of the problems, like fighting human trafficking is one of them. I believe there's a deep interest here in social work. I saw that up front. And we're always looking for good research collaboration, especially in these times, right? I heard you allude to that, and it's true for all of us, right? We're all looking for ways to adapt, right, to the current environment. So these are just some of my students. So Kay Shen, you see right here, she's just graduating this semester with a PhD. We also have a new PhD student joining us, and these are some of my existing PhD students who are entering their second, third years. So we have a nice tight group, and we also have undergrad students and MS students, sometimes from other countries who come visit us during the summer, which is a lot of fun. So these are just some pictures to showcase the group. And here are some of the research projects where I've worked on either in the recent past or even right now. So you'll be seeing a little bit about the human trafficking and the patient-centered healthcare, I think, today. But there's also a lot of other projects, and I'm happy to talk about some of them. There are questions, but they're mainly funded by DARPA, also by Microsoft Research, Kaiser Permanente. The human trafficking work was originally funded by DARPA, but it has since been funded by philanthropists and others. So this is something that we really want to keep going as long as possible. And all of these projects, involve, broadly speaking, AI, but narrowly speaking, that there's a huge text component to all of these projects. So we're often working with a lot of text data. We're sort of less in computer vision. We don't do work directly in images and computer vision, but we collaborate with people who work on computer vision on some of these projects. And one specific area of research and of AI and text analytics that I am very interested in is knowledge graphs. How many people have heard of knowledge graphs? Anyone? Yes. Where have you? If I can cold call you, where have you heard about it?
I mean, I guess I've heard these things sort of kicked around in various sort of, I guess, data science sort of spaces, and it's sort of how different domains or areas and ideas are connected with one another. And they're kind of used in a variety of spaces.
Yeah. No, very good. That's right. And I'll show you some examples, later on why knowledge graphs are sort of a very useful medium for thinking about a lot of different projects. So it turns out like if you can construct knowledge graphs and if you can reason with knowledge graphs, there are a lot of problems that you can solve in any given domain. So I'll say a little bit about that, but a lot of our work, both serious and non-serious, we also like to work on fun things, which are not so dark, right? They do get covered a number of times in the press. So for example, in popular science, we had this coverage of a journal article we had done back in 2020, 2021, where we looked at all the Twitter data before it got bought by Elon, right? And we trying to understand how emojis are being used all across the world. We were like, this is like a different form of language, right? Which has not really been studied, and so this was one, other things are, we looked at literature, to see like male versus female representation. The news was not good, unfortunately, right? But perhaps not, it was unsurprising, but not good, and not much has changed, unfortunately, over 100 years. And we also look at things like, money networks, how do rich people hide fortunes offshore, right? And we've done studies on this using network analysis and so on and so forth. So you see a range of things over here. All right, so jumping into the fundamental material, right? So this is just a range of things that we worked on. But before I go deeper into some of the projects, I want to just begin by, sort of telling you what we mean by text analytics, because it's a very broad term and, it is synonymous, some would argue not, but I think especially now with the large language models like ChatGPT and Claude and so on, these terms are becoming more and more synonymous, so when someone talks about text analytics or natural language processing, I mean, they by and large are referring to, a similar set of techniques and communities, although their specialization maybe in sort of narrower areas of these broad, techniques or broad areas of research. So yes.
Can I clarify? So large language models now, like ChatGPT, are open. It can do data analytics, but often also used for text generations.
Yes.
So when you are referring to text analytics, do you also refer to generative text or just
yes
analytical purpose, like for identify patterns and maybe?
Yeah, that's correct. So generative AI is included in practice, pretty much within text analytics. I think that the reason that it's not that you were not included in the past, I think what happened was it's a very hard problem. So until recently, that there was no progress on the generative AI, right? It was only since 2022, 2023 that we saw this Cambrian explosion in generative AI, right? And so so it didn't belong anywhere because it was kind of like nuclear fusion, right? Like so, but it's become like that. So yes, it does fall under NLP, text analytics, all of those things. Yeah. I will sort of stick a little bit to NLP because I think that is maybe the term that is more broadly used now. But in ISC, we like to use text analytics because we're very interested in analytics per se. So NLP is the branch of computer science that is focused on developing systems that allow computers to communicate with people using everyday language. So this is a very simple definition, but it still is the vision behind natural language processing, even today. So allowing computers to communicate with people, right? I mean, the question then becomes, okay, what do we mean by communicate? And it turns out there's a lot under that, right? The computer has to understand you, it has to understand the context, then it has to communicate with you in a way that you understand, right? And so it's not just that, it's not just a one-sided thing. We want a bi-directional communication that takes context into account and all kinds of things into account. So this remains a very hard problem, although there has been significant progress, especially since the large language models. And there's a related field, which is computational linguistics. This one is, how do we understand human language using computational methods? So this, typically there's a division in Dornsife, I believe, that studies this. For example, some work in this would be understanding morphology of language over time, or how is language on Twitter different compared to Reddit, that also kind of would fall under computational linguistics. Whereas NLP is more on systems building, traditionally. It's less about understanding human language. It's more about building systems that understand and communicate using human language. So there's a more engineering side to it than the computational linguistics. But all of these areas are related. I think we are living in a time where all of these areas are coming together. The boundaries are not delineated at all. So, everything from philosophy of language to cognitive science. I mean, we see a lot of people from cognitive science publish in NLP. We see NLP people publish in cognitive science and so on. So it's not, people are not jealously guarding their areas. In AI and computer science, they are very open, in fact, to new voices. And it's one of the really good things about the field, where they really don't, it's not like, okay, this person is not in our field, so why are they writing articles in our area? It's totally the opposite, in fact, in AI. So key questions underlying NLP and text analysis is, how can we make a machine really understand text? And by text, we often mean natural language, right? So this is not, this is language that has been generated by humans, usually, whether it's Twitter data, whether it's, complaints that have been submitted to the government, whether it's advertisements on the web, for human trafficking, there are sex advertisements that we use in our studies and so on. So how do we make a machine really understand what humans are generating? And this is kind of more of the analytics part. And then, of course, there's a generation part, which is how do you get the machine to respond back, right, to a question that a human might be asking? And context is really important. This idea that, text is not just what we call a string. Historically, right, from the machine's point of view, text is really just a list of characters. So you have, like, for example, if I say, like look at this phrase here, like things with properties, right? The word with is not just a list of 4 characters, right? It is attaching, it is telling you that there are things and things have properties. And so with here is connecting things with properties, right? It's telling you something about things. So this is a very specific kind of word. But also if I say, okay, I want to work for Apple, I want to eat an apple, right? So that the meaning of the word apple is changing depending on that sentence. Sometimes you cannot make out just from the sentence. You need you need a paragraph before that to really understand, what a word, a phrase, a pronoun would be referring to. So the context is really important, and it's hard, right? Like, how do we get a machine to do that? We can't really reverse engineer the brain. And we don't even know how humans, I mean, there's a lot of questions about how humans understand. So this gets to the heart of the philosophy of language, for example, and all of those things. But that's what we are aiming to do. So here are some example problems in text analytics and NLP, so very specific problems. So you have a question like this, which seem very obvious to us humans, and it turns out it's hard for machines. Until recently, the machines were not good at answering questions like these, which is like something like this. Sometimes when we don't get enough sleep, we become very short-tempered. It is important to set a time to go to bed that is realistic. How are these 2 sentences related, right? The first sentence explains the meaning of the second. That's not quite right, right? The second sentence proposes a solution that seems to be more correct, right? But notice you're thinking about it, right? And it comes very naturally to you, right? It's very natural. It's not like writing a program. It's not like, it's not something that is really requiring you to draw on skills in some sense. It just comes natural. Even someone with a high school education would probably be able to do this, unless the sentences are very complicated. The second sentence explains why a lack of sleep affects us. The second sentence contradicts the first. So it's clearly the second option. The second option is correct, right? And we don't really need special skills to do this, except in very hard cases. This is natural. This is why this is natural language and natural reasoning, right? So all of these things come very naturally to us. And that sort of leads to this paradox often in AI, that things which are not so natural for us are actually easier to program in machines. So this is why something like playing chess is much easier for machines to do than comprehension. Comprehension is much harder. Even though for us humans, we would say, okay, I can beat Gary Kasparov, then I'm a genius. But in fact, machines can beat Gary Kasparov and have been able to beat Gary Kasparov for like 30 years now, right? But they cannot do this, and other problems that 7, 8-year-olds can do even. So this is a paradox actually in AI and machine learning, but it makes sense once you begin to understand that the things that we take for granted are in fact the superpowers as humans. So text summarization is another one. This is a generative problem, right? So here I'm giving you a longer document, and let's say I just want a 1-sentence summary. Now this used to be a very hard problem. It has become a lot easier since ChatGPT, right? But this also falls under text analytics. Others are question answering, much harder than it looks. So, if I ask you a question, how many presidents have there been since Barack Obama was born? The reason why this is an interesting question, compared to something like when was Barack Obama born, is that you can answer a question like when was Barack Obama born by looking up the right Wikipedia page. And if a machine looks up the right Wikipedia page, and they will find the answer, right? But how many presidents have there been since Barack Obama was born? Unless someone has explicitly answered this question somewhere on the web, this requires reasoning. Right now, what kind of reasoning do we need? First, we need to figure out when he was born, right? So that we have to look up, right? Unless you know it. And then you have to figure out how many presidents there were by making a list of the presidents and then counting, right? Because some of them were there for 2 terms, etc., right? And so you need to count that. So there are 2 or 3 steps. This is what we call multi-hop reasoning. Now this one is relatively easy because it's just looking up pieces of information and then counting. But you can also have more difficult types of reasoning, and we in fact have to do that in our everyday lives, right? Where we are reasoning, you're trying to plan a party, but someone is a vegan, someone might come late, someone might be out of town, there's probability involved, how uncertain is the information? How do you plan the party? When do you call them? What food do you order? Those things are planning, reasoning, still very difficult for AI, even for ChatGPT. Another problem is semantic role labeling. So this one is different from syntax. So there's syntactic parsing. For example, this is a preposition, this is a noun, this is a pronoun. That is a little bit different. That problem is solved now. But semantic role labeling is we want to understand the semantics behind the words in the sentence. So usually what we do is we want to assign roles to them. And when I say we, what I really mean is the algorithm. We want the algorithm to do that. We don't want to do that, right? So we want the algorithm to tell us, well, okay, John here is an agent, what we call an agent. Mary is a patient. Now by patient here, we don't mean a doctor's patient, right? A patient here typically means a passive entity from the sentence point of view, right? That this is not like the main person driving the sentence, but they are a participant in the sentence, right? They have some kind of participation. And so that's what patient here means. From Austin to Dallas, source, destination, instrument. Again, instrument is not just, instrument as we would think about it. It is just any device or mechanism in the semantic role labeling framework that is used to accomplish something, right? So in this case, Toyota Prius is the instrument and similarly, hammer is the instrument. But you can see hammer is not the agent. We would not say hammer is the agent, right? So if you use simple rules that, okay, if X, verb Y, then X is the agent, that it doesn't work. It turns out that is what makes natural language really hard. You can't write rules. People tried that, it failed. The rules keep growing and ultimately there are contradictions. It turns out, it's just the way that we speak, right? We are not programming languages. We don't speak programming languages. We really play with language, right? That's the whole basis of literature, of culture, of poetry. We like to play with language. And it's not difficult for us, right, to switch to totally different ways of communicating, like Twitter. Textual entailment, right? So we saw this already a little bit, where you have one sentence, you have a text, you have a hypothesis, and entailment is, okay, is the hypothesis true or plausible for the text? So I'm the huge market potential currently led by Google. Yahoo took over search company Overture searches last year. The hypothesis here is Yahoo bought Overture. They define hypothesis a little bit differently. It's not quite a scientific hypothesis, but here it would be true. But then there are other cases where it's false. So we want the machine, this again is about understanding. Does the machine understand the text and the hypothesis together? right? To be able to answer this question. Then there's Anna for a resolution. This is really interesting. I often give this to my students in the class that I teach on text analytics. So today was Jack's birthday. Penny and Janet went to the store. They were going to get presents. Janet decided to get a kite. Don't do that, said Penny. Jack has a kite. He will make you take it back. Now, we don't even have to think, what does he mean over here? Right? But clearly he is referring to Jack, and it is referring to the kite, and you is referring to Janet, right? But if you're just looking at this from a machine standpoint, right? How does a machine know that he is referring to Jack and you is referring to Janet and not Penny, etc.? Right? Again, if you try to just write a program, it's very difficult, right? There's no program that will actually get you this. You can try to use a rule, like for example, if you see a pronoun, then maybe the closest noun is a thing that matches. Now that will work here, right? But it turns out that you can, and this is a fun exercise, you can actually change the sentence so that no matter what rule I give you, the rule will then give you the wrong answer in this case, right? So I could say, for example, I believe Jack has a kite, or Michael said, or that's what Michael said, right? Or something like that. And so now it's like, okay, Michael is not he, right? Assuming that he is still Jack. So you can actually, modify the sentence and really play games with it so that it's no rule is actually going to suffice. So we need something much more complicated than some kind of rule. And yeah, here's just like, a bunch of examples. And finally, a problem that we are very interested in, and that I think is also hopefully of interest to you, and I'll show you why, which is called information extraction. So this is where you get a big piece of text. It could be a PDF, it could be a paragraph, it could be a sentence. And what we are trying to do is to extract entities from the text. So these could be people, places, organizations. In some sense, what we want to do is convert the text into a database, right? So like a database is something like a spreadsheet, right? That's one way to think about it. It's again more complicated than that. Like Oracle, for example, has big financial databases, that they provide services to banks and so on. But all your student records, for example, all your grades, right? When you pull up on the OSIS or whatever the system is and you request a transcript, like there's a database, right? They issue a query to the database, and then the responses come back and they show that to you on a screen, right? Similarly, when you are querying your bank records or any other thing like that, a spreadsheet, right? The database is structured. That's the key point to remember. It's not text, it is structured in columns and tables and graphs, and it has structure, right? But the PDFs and the text is not structured. It is natural language, right? We get it, but for the machine would be much better off if it can instead look at that as a database, right? So how do we convert the text into a database? That's kind of the information extraction problem. And the moment you do, then suddenly a lot of possibilities open up. Because to give you an example, we are looking at a project right now with the CFPB, the Consumer Financial Protection Bureau, which is under danger of shutting down, right? The current administration is trying to shut down the CFPB. It was created right after the 2008 crisis, right? I believe by Elizabeth Warren was a key stakeholder in the CFPB. And basically you can submit complaints to the CFPB if you believe that you are a victim of some kind of financial or consumer fraud. So, student loan frauds and all kinds of frauds can be reported to the CFPB. And they have a long list of complaints, which they have made public. Like they scrub the information, they ask you whether you're okay with this being made public, and then they scrub some of the information, and there's a long set of complaints that is actually public. We don't know obviously who it's coming from, they have maintained privacy, but we do know the content of the complaint sufficiently de-anonymized or anonymized. And so, some of the questions we want to ask are things like, what are sort of the key financial institutions that are implicated in these complaints? So what is the specific type of complaint, or and things like that. And so it turns out to answer those questions, you have to first extract entities from the text. Only then can you answer. Because you have to first extract it, then you're issuing an aggregation query where you're doing things like counting and so on, right? Because you have to look at the whole data. If I'm asking you, okay, what is the main financial institution? You can't answer that using one piece of text. You have to look at the whole corpus. right? To know who's number one, what is the number one financial institution. So that's just one example, but there are many others. In all our projects, we actually use this. And then the easiest thing that maybe you're likely to be familiar with is a problem with text classification, is something like spam classification, right? Where you get emails and the system, your inbox is typically classifying spam or not spam. It's looking at the text, it's looking at who sent the email and a bunch of other things. But this is like the very first application, actually, one of the very first applications of text analysis. And then so on and so forth. Sentiment analysis, this is very good for people who are doing social media analytics, right? Like, is my if I'm advertising something, how good is the sentiment? Are people looking at that? Are responding to it positively or negatively? And so on and so forth, right? So this is what I have on the what we do, right? So these are all the whats of text analysis and the natural language processing, all the different problems we solve. Now, every single one of those things that you saw has many algorithms behind it. We have entire research communities behind it. So the how is very complicated, right? So that's kind of what we do research on. But the what is not that difficult to understand, right? Like, what is the problem that we are trying to solve? This is really easy, but the how is very difficult. So this can sometimes cause a disconnect because we get a question, well, if it's that easy for us to understand what the problem is, surely it must be easy to solve. But like, unfortunately, no. It's very hard to solve, and that's why we have AI, or we want to develop AI, because we're replicating things that we find easy. So with that, let me try to jump a little bit to examples from my own work, just to make sure I'm keeping a watch on time. So I want to start with the crisis response system. So this is a system that is called THOR, so it's easy to remember, text-enabled humanitarian operations in real time. And the specific problem that we were trying to solve is what we learned, and this is true even today, perhaps more so, but even before ChatGPT and so on, what we learned was, unsurprisingly, that the major Western languages, right, like English and French and so on, there are a lot of computational tools for those languages, right? So, but for what we call low resource languages. So these are not low resource in the sense that very few people speak them. Actually, many millions of people speak them. For example, Uriya, right, which is a language in India, tens of millions of people actually speak Uriya. And that's true for many other languages also. But whether it's a small number of people or a very large number of people, there is a big part of the world that speaks low resource languages, low resource in the computational sense, that we don't have tools for these languages. Right, so it's they are not able to use the advances that are happening for English and some of the other major languages. Now, the reason why this was of interest in this project is that let's say when an earthquake breaks out in Nepal or in northern China where they speak Uyghur and so on, the Red Cross or aid agencies come in, but no one really speaks the language. Right, so they are not able to understand, where should we send resources? Where is the building coming apart? Where is there a water shortage? Where is there a food shortage? Where is there risk of violence? Now, it's not that the information is not there, because typically when the disaster breaks out, everyone now has some kind of phone or smartphone, even in very poor regions, and the governments usually set up hotlines. So you can actually message to the hotline, and many people do, right? That's their only way to communicate in many of these regions. Or they're texting their hotlines. There's a platform called Ushahidi, that was designed for election violence in Kenya, to report instances of election violence in Kenya. It was an open source project that has since been extended to many other countries and adapted for many other countries. So the data collection is there. There are ways to collect data, but they're in the local language and they're very short, right? So how can we make sense of all of those messages? That was the fundamental question of this project. So specifically for northern China, right? So this is Uyghur. And as you can see here, there's a whole stream of messages coming in and we don't really understand what's happening, right? There's a long stream of messages. So instead, if we can do something like this, right? Where you can see here that to populate all of these different dashboards, you actually need to first do machine translation. You need to translate these to English, right? So that has to be done very quickly by the algorithm. Doesn't have to be perfect. The second thing that needs to happen is information extraction. Because you cannot populate a map like this unless you can extract locations. Right? So if I am saying, okay, I like my building in this neighborhood is collapsing. I need to extract that building and then geo-map it, and then I can put it on this dashboard. And you can also see that, we also want to do text classification. So the text is very small over there, but basically all these colors are need types. So the blue one is medicine, the green one is shelter, purple is food, and so on. So we're trying to classify what need is this message expressing, if any. This is text classification. It is similar to the spam, right? Like you get your email, you're trying to understand is this spam or not. Technologically, this is similar. You have 6 or 7 categories. You're trying to understand which category applies to which message, right? But the message is very short. It's in a foreign language. It's very noisy. So it's much harder than the email, right? Which is longer. There's a lot more context. So let me show you how this works. So there are several use cases here. One of them was Mozambique, which was for AFRICOM. AFRICOM is an agency. And this one is in English. We took a lot of data from Twitter just to showcase, how the system works. And again, you can sort of see here the text, right? We want to extract here. Again, we have Uyghur, right? So it works for foreign languages. We extract locations. We extract needs. That's what the different colors are, the different needs, right? And the visualization is interactive. So you can actually click on different colors. You can draw the bounding box, as you see over here, and it will like zoom in. And one of the reasons why this is important, by the way, is that it allows us to deal with noise. So we are building for human beings. This is not the whole automated system, right? We want a first responder to go in and use the system. And even if it's noisy, right, we want them to work with the noise. We're not looking for 100%, right? We're saying you can look at the data. You can draw the boxes, you click on things, there's going to be noise, we'll extract locations, which are not really locations and so on. But this is better than, translating and reading 10,000, 20,000 messages, right? So that's kind of, we're trying to build those kinds of systems. That is very important in our group. So not just algorithms, but how do we make them work in a real system for real stakeholders? So, the architecture is very complex, right? So this is a little bit of the how. There are lots of modules, lots of things happening here. It wasn't just our group. There were multiple groups that were actually working on this and so on. But, if you think about it from the beginning to the end, everything begins with the data and it ends with the interfaces. In the middle is a whole bunch of things that have to happen. So these are just some of the features of the interface, right? So aggregated profile of needs and situation types, clickable entities, you can click on these things and it will show you relevant entries and the places in the map that correspond. There's the original text, this could be in a foreign language. There's the information extraction, right? And that's how you're getting this thing that looks kind of like a spreadsheet, right? And so on. And then the other one is human trafficking. I'll just go very briefly over this. So it's a similar problem. So again, human trafficking, it's a really terrible problem. It's the fastest growing business of organized crime. There are lots of facts. I think we can all agree it's a huge problem. It's a worldwide problem. It's also here in the US, unfortunately. It's not just, a quote unquote poor country problem. It turns out there's a lot of money here, right? So it also occurs a lot in rich countries because the market is huge, unfortunately, right? So what we were trying to understand is how can we use design science research principle, that's what DSR stands for, to make large scale investigative search easy, useful, and efficient for human trafficking investigators. Basically, if someone goes missing, like if there's a missing child or a missing person where we feel, or the investigator feels that the person might have been kidnapped or is being trafficked, can we find that person very quickly? I mean, ideally, we want to find them before they come on the web, but at least the moment the first advertisement appears on the web, assuming that usual ways of finding them have failed, the on-the-ground ways have failed, they've totally disappeared, right? But there's some reason to believe that if they are being trafficked, eventually the ad will appear somewhere on the web. Because just like all advertisement, the web has been used to also advertise for this, even though it's a very physical business. But this is how the matchmaking occurs between a victim or in other cases, a sex service provider and the person who is contracting the sex service, right? So the actual service is physical, but the way that they connect is online. They get the information online, right? So there are lots and lots of advertisement. And again, you see the information extraction problem show up, right? So you have this advertisement, but if we can extract all this other stuff that you see here, then we make it easier for the investigator to find the person that they might be looking for. Because let's say by accident, they are using the phone or a different phone, and we have reason to believe that they have a burner phone, then they have another burner phone. If we get a lead, right, where is this phone number showing up, right, in this domain? Sometimes what happens is that there are physical descriptions, that we could search for. We might have reason to believe that they might be in a certain location, and as a physical description, right? So it's a very dark domain, but ultimately we want to try and rescue victims. So, this is one of the use cases. So in this case also, we built this interface, we extracted a lot of information. We then transitioned this to the New York Human Trafficking Resource Unit. And they in turn made it available to a lot of law enforcement all across the US. And the goal was always to find human trafficking victims, to rescue them, and then in some cases to find the traffickers and to prosecute them. And that also happened in a number of cases. So here you can see the San Francisco District Attorney said we literally couldn't do what we do. MEMEX is the overall program that funded this research. It's indispensable to bringing sex traffickers to justice in Manhattan. You see some examples here, very horrific examples, but they would not have been able to collect the evidence for these cases without the system. So it has two use cases. So this is where this project began. This is what we did for 2016 to 20. But then, we switched to other research, which is still ongoing. We are still very much involved in this, me and my PhD student, where we want to do sense making. We're now looking at this as, okay, we built the system, ultimately we cannot do anything more than that. The law enforcement and others have to now figure out a way to make, to prosecute, to find, to do what they are doing, right? But can we at least understand what is happening here? Why is this happening at this scale? What are preventive measures that can be taken? What can we learn about this, right? What are the scientific findings that allow us to understand and hopefully do better from a policy standpoint, right? So that is what we have moved towards. And this, what you're seeing over here is literally the first large-scale network. This is a real network, the first large-scale network of sex providers who are connected, across all the advertisements, because sometimes they post together, they use the same payment information and so on. And you can see it looks very intriguing, right? You see some really big clusters. You see sometimes clusters coming together. We are guessing that the big clusters here, the star clusters, are actually trafficking rings. The smaller clusters are probably independent sex workers, who are socio-economically desperate, right, in many cases, but they are not necessarily being trafficked by someone. So we do distinguish, you have to draw these subtle distinctions, which is very important, because not everyone is being coerced physically, right? And so we're looking at all of these questions. We are about to submit a paper on the ASEAN countries, which is like Malaysia and Philippines, and all those countries, the Golden Triangle, we call the ASEAN countries, ASEAN, all in capital letters. And we just finished a study on that we are going to publish very soon. On the policy front, this is really important. We often participate in, wherever we are asked. I mean, basically, if we're told, hey, can you come? Can you give a talk? Can you talk about this issue? I always say yes, no matter what is happening. So that is kind of, what we have here for, the text analytics and some of the work that we do. I know we're running out of time. One of the very few things that I just wanted to show you maybe in a couple of minutes is, our healthcare work, right? So this is work that we did with Kaiser Permanente. I briefly mentioned it. The reason why this is interesting, why I wanted to show you this, is sort of an example of why knowledge graphs and semantics is really important. So they have the system called FDL, which is called Finding Doctors and Location. So the idea here is that if you're looking for a doctor or location within Kaiser's network, right? So let's say you go in and you type something like urinary tract infection. What you really need is a urologist, right? But you're not typing in urology. You're typing in urinary tract infection, or I might type in heart doctor, but what I'm looking for is a cardiologist. And so we're not doctors, so we don't know all the terms. We don't know which doctor treats which organ or which condition or who I should see and so on. So in this case, we built a system for them where you can type in something like urinary tract infection, and we use natural language processing and knowledge graph and so on to figure out that in fact what the patient wants is a urologist, and then to return that result to them. So that was kind of this project, and the way that we do it is to build a knowledge graph. And this one slide, I think, kind of shows you how it's done. So let's say you have this EHR feed, electronic health record. It has a very complex piece of, oh, sorry, sorry, I didn't realize that I was. No, oops, I should have looked sooner. So, sorry, the FDM that I was talking about, and I know we're almost out of time, but it's like, this is what it looks like. Like you type the urinary tract infection and you get a urologist. So it's a very simple web interface. But on speaking of the knowledge graph, right, I think in this slide, right, what you can see is you have these electronic health records, right? And so this looks very complex, kind of the thing that your doctor would write when you go in. But what we really want is to extract this graph or this database from this, where we want to understand, okay, these are the symptoms, this is the diagnosis, this is the lab test, then we want to connect all of them. And so if you're able to do that, then you can now start to look at the whole data set, almost like a database. This allows you to do a lot more. The reason why I wanted to show you this is that it's possible to do for almost any domain that you might be thinking of. So if you have text data and you feel that you would benefit, right, from a knowledge graph or from this kind of text analytics, that we have all the tools to actually do that very easily. So we're always looking for interesting domains to collaborate in. And you can see that a wide range of domains, crisis, human trafficking, healthcare. We're not the experts in the domain, but usually we are able to talk to the people who are the experts, figure out what they need, and then apply the tools to get them what they need to build something more useful. And just fun fact, by the way, like all of these companies have knowledge graphs. I haven't shown Google here, but Google was the first one to actually come out with a commercial scale knowledge graph. It uses it for search engine, but Amazon has one. So when you search on Amazon for product, they use a knowledge graph to actually figure out what the products are and so on. And now Kaiser Ninja also has one because of the collaboration that we did with them. So I will stop sharing. And I don't know if there are questions. I think there's something in the chat. Oh, which emoji is it? Okay, so I'm guessing maybe you're asking what was the most popular emoji that we found in 21. And yeah, it was the one with the tears streaming down the on the face. And which has like very interesting meanings, right? Like to ask what that showed was that emoji communicates a lot of different things depending on which sentence it's been placed in. I mean, I almost wish, that paper had been published now, because for all of you who are following this whole Blake Lively saga, right? I don't know, a lot of people who are not following it. It's really struck off a firestorm, even among people who don't follow pop culture. The whole thing started with emojis, actually, right? Like if you follow that case, the New York Times published all these text messages and they removed the emojis. Right? It turns out if you add the emojis, the text messages totally change in meaning. Right. So it came out now, but we were like, okay, we were pointing to that, from a study point of view, in like 2020, 2021. But that was like a fun study. Yeah.
So we've got a couple minutes. Any questions from the in-person audience? Online?
Yes.
I
Go ahead, please.
Just something regarding the emoji concept, knowing what you have known now, right? Back with that context of when that popular emoji was. If we're gonna break that down to that today, that emoji is used in like 10 different interpretations. So like happy to sad to like over, like how would you then kind of do that in a system where it can give you all.
Can distinguish. It's a great question. I think that it is a study worth doing. I don't think anyone has done the study, but how we would do it is that we would first get all the social media or the messages where that emoji is showing up. So let's say, just for the sake of simplicity, there are 10,000 tweets where that emoji is showing up. What we would now try to do is apply a text analytics method called clustering. So what clustering does is that it tries to it tries to divide the units into groups, exactly what it sounds like it's trying to discover clusters, but the clusters are based on the actual text content. So we have machine learning methods that can take the text content and we're trying to break it into groups. And then the hope would be that each group is a different interpretation. And then we would like look at all the clusters and we would like sample some messages, and then we would be able to say, okay, these are all the different interpretations. And that actually would be a paper in itself to say that we did this large scale study and here are all the different interpretations that were learned from the machine learning.
And I just as a question / comment to that, I mean, these text clusterings that you do are inherently based on the same sorts of clustering methods that we've been using in statistics for the last 30 or so years. They're just being applied to language at a large scale. Is that true? Because I think one of the things that people in social work oftentimes have a trouble knowing is how to make the connection between the sorts of statistical modeling that we're taught
Yeah.
in the social sciences and this what almost seems like magic that's happening with natural language processing, when in fact they're under the hood, so to speak. There's a lot of
There's a lot of
similarities.
similarity. It's a great question. I'm so happy you asked that. So let's continue with the text clustering example to
Mhm.
understand what the overlap and connection is. So you're right that the clustering algorithm is, I would say it's come from both statistics and machine learning. So like, there are some algorithms that were designed by the machine learning community. But here's the real problem. So the problem is not so much with the clustering itself, but how do you convert the text into a mathematical representation that the clustering can then be applied on?
That's right.
So, if you think about a 2D space, very simple, right? Which is, okay, so I have a piece of text, but the clustering is assuming a vector or a point, let's say 2D space, but in reality, it's a 100-dimensional space or something like that. And so how do we go from the text to that 2D space? This is a field of machine learning that is called representation learning, for obvious reasons, that you're trying to learn typically a mathematical representation of the unit, whether it's a text, whether it's an image, whatever it is. And that is where I think a lot of the innovations lie. And so we kind of teach in the class, what we do is that, we actually start with a very simple representation, then we go on to a more complex representation. But like now what people do is that with the deep learning, the neural networks, the neural network is actually learning the representation.
Right.
And that's why it's so good, because it's able to, use all the layers and the neurons and the complex mathematics to learn the representation. But that also leads to another problem, which is that now the representation becomes non-interpretable.
Right.
It works very well, but when on the occasion where it goes wrong or it does something stupid, as you see with hallucinations in large language models, we can't really explain what happened. Why did it give us a hallucination? Why did it make something up? Because that's kind of because we cannot understand the representation anymore. So that's the price we are paying.
Yeah.
It's almost like some people believe it's like a Faustian bargain that machine learning and AI has made. And can we unwind the Faustian bargain? We're all trying. We're trying to unwind the Faustian bargain, but we have made a Faustian bargain.
Yeah.
In AI, which is that, okay, we are going to get 99% performance or 90% performance, but in exchange, it becomes magic.
Right.
Effectively.
Right.
Yeah.
No, which I think is really something that when at least the folks that I've been working with in social work, when we're collaborating with people who are doing, data science, be it large language models or just using these neural networks, I think this is oftentimes the exchange, which is that traditionally in social sciences, what we want to know is not just the accuracy of a prediction, but we want to know why that prediction was made.
Right.
And if you don't have a good rationale behind why, then essentially we almost, traditionally at least, would throw up our hands and say, well, we don't care how good the prediction is if you can't tell us why,
Right.
because inherently we've been interested in hypothesis testing, which is
Yes.
all about why.
Yeah.
And so it's a really, but yet to be fair, the preference for why and hypothesis testing is not truly where we've been at. We really do want to know.
Yeah.
We want models that are good performers, and so it's a really interesting thing for us.
Yeah,
to
it's a
wrestle.
back and forth because on the one hand, it's very good for exploration, which could then help you to generate the hypothesis. So that is one very good use case. But the other one is there is a lot of work happening now, and this is some of our AI projects, where we are trying to understand the why. And it turns out there are ways to prompt the language model and do work with the language model so that it's able to give you a fairly decent rationale for why it's doing something. So I think that is becoming more and more possible. I think that for a long time, it's true that we could not get beyond that, either you get good performance or you have less performance, but you get the Y. But like now I feel like we can have both, like we are making our way to a world where both might be possible through the system.
No, and that's really exciting. I mean, because
Yeah.
that's where I mean, ultimately, it would be great to have, both an explanation and performance, right? I'm conscious of the fact that we are running out of time, but is there anyone online who wanted to ask a question? Okay, all right, well, let's all give a round of thanks again. It's been a great and really interesting talk.